Hello everyone. In this week's lab, we'll be solving nonlinear equations using open methods. In this video, I'll be solving with you an example using the Newton-Raphson method. First, I will give you a brief recap on the Newton-Raphson algorithm. Then I'll show you how to create a simple MATLAB program for it. And then I'll be talking about the fixed point iteration, particularly in terms of its convergence criteria. And finally, I'll be giving you some concluding remarks and assignment tips. In the Newton-Raphson method, you start off by defining x naught, your initial guess, and your input function f of x and its first derivative f prime of x. And you also need to define an error threshold and the maximum number of iterations to control your loop so that you don't end up with an infinite loop. Once you define these parameters, you can estimate the new root using the Newton-Raphson equation and your relative error. Based on the relative error and the current number of iterations, you decide whether to proceed with the code, like to do another iteration, or you decide to end the code. So the type of parameters that we have, x naught is just a constant, f of x is defined as a function, f prime of x is also defined as a function, e of s is defined as a constant, n is a constant, I is an index, it's a variable that changes with each iteration, xi would be defined as an array, and e of I would be defined as an array, in order to compare the results between each iteration. So let's apply this algorithm to a simple example. Let's assume that we have a function f of x equal to tan pi minus x, and let's assume we're interested in finding the value of x where f of x is equal to 2.5. The first thing that we do when we have any nonlinear equation that we want to solve is to graphically inspect it. So I plotted the function, as you can see it, and this is the constant value of 2.5, and from the intersection we can predict that the root is around the value of 1.8. So we then need to rearrange the function in such a way that the 2.5 is moved to the left hand side, and then we can proceed with the rest of the algorithm. We can calculate the first derivative, which in this case would be minus sec square of pi minus x minus 1, and we need to set some values to x naught. For this case I chose to be 1.7, for the error threshold, and I chose to be 0.001, and n, which in this case is 1000 iterations. And now we can start solving the problem on MATLAB. So I started a new script file. I'll give it a brief description. Newton-Raphson method. You should also include your name as we stated before. Maybe your ID and today's date. And a brief description of what the file does. What the code does, I mean. Uses the Newton your equations. Okay. In the first step of the algorithm, we needed to define some parameters. So I gave a subsection called definitions, and I'll first define the initial guess, and in this case, like I said, it's 1.7, which is the initial guess. And I will be defining a function, and as we stated in lab 2, this is how you define a function in MATLAB. And my function is tan of pi minus x, and I need to account for the fact that I moved the 2.5 to the left hand side. So this is my input function after rearrangement. And I need to define my derivative as well. I'll call it f sub dot. In this case it will be the function minus of secant squared, and this is how you write secant squared in MATLAB, minus 1, and we need to define the error threshold, and then the maximum number of iterations. First derivative and error threshold max number of iterations. Before starting the loop, we need to initialize some values. In this case, I need to initialize I, which is my index, and I'll give it a 1. And E of I, E is the array that I'll be using to calculate the error for each index or for each root. And the first one, E of 1, will be equal to 1. And X of I, which means that the first element of the array would be the initial guess. Please note that these arrays have variable length, and their size depends on the number of times that the loop is executed. So this is a variable sized array for storing the error for each I. And similarly, this is a variable sized array for storing the root for each I. And then we can proceed with our loop. It will be a simple while loop in this case. The loop. So it will be a while, and like I said, it has two conditions. First one is I less than n, and in this case I was initialized with 1, so it will start. And then we have an AND. The error threshold less than the current error. Okay. There is a missing parenthesis, so you have to be careful with this. Okay. And then we need to calculate the x for the next step. And here I'm saying that for the next step, or for the next element in the array, store this equation or this evaluated value x I wrote the expression for the error somewhere else, so I'll just copy it to save time. So like I said, these two parameters are variable sized array. With each execution of the loop, you'll be storing a new element in the array. And we'll need to update the value of the I. And then we need to do some formatting for the output. I will be producing the results in a table, so I need to define a new array just for the to record the number of iterations that we had, because I was just a single variable. And froot, I would be simply evaluating f of x for my array of x. So this array just stores the value of f of x for each of x that I stored in this array. And then I will be defining a table. I call it tab, and then the command table can be written this way. Just be careful that when you are plotting things in a table, it has to be defined as a column vector, not as a row. All of the arrays that I defined were defined as rows, so I need to convert them using the transpose command so that it can be written as a column vector. So transpose of x, transpose of e, and then transpose of f root. And then since I want my table to have headings, this is one of the options of the command, is to write variable names like this. And then using the curly brackets, you give your titles. In this case, it will be iterations, the root, and the error, and f of x, f of this particular root, I mean. And then we can display the output, so I can call it table of results. And I can display the table. So now when I run, I need to save it first. So I'll save it. So I call it lab3. And now we can run, and we can see that it was able to converge in just 6 iterations. The final solution is close to what we predicted. We predicted that it would be close to 1.8, so it's 1.7993. You can see that the error is almost 0 in this case, and that the value of the function, of course after rearrangement, is equal to 0. So the results are good, so we can be confident with our results. So similar to the example that I've just shown you, you can extend it to the fixed point iteration method or the secant method. You just have to remember that for the fixed point iteration, you need to convert xi plus 1 equal to g of xi as stated in the lecture notes. And you should also remember that its convergence depends on the initial guess x node and the form of g of xi in such a way that g prime of xi, the absolute value of it, should be bounded by 1. And based on those two parameters, the behavior can be a monotonic convergence, an oscillatory convergence, a monotonic divergence, or an oscillatory divergence. In the assignment, you're already given the form of g of x, so you don't have to worry about it. But you need to compare the performance of each form. So you can do this in a number of ways. You can compare the number of iterations required to converge, if it converges. You can compare the error and how it changes. You can compare them by plotting g of x and g prime of x and state how these parameters are affecting your convergence for each form. You can also rely on the plot function, which you used for assignment 2 to plot any relevant function. You don't have to plot everything, to write a new code for plotting the functions. So I wanted to conclude this video with some closing remarks and some tips for the assignment. So when you're dealing with solving nonlinear equations, you have to be careful. If the problem has a physical meaning, make sure that the root that you're getting is physically meaningful. For example, if we use f0, which is the built-in MATLAB function for finding roots of nonlinear equation, for our problem, with initial guess of 1.7, you get this value, 1.571, which is pi over 2. And actually, for this particular function, pi over 2 would give you an asymptote. So it's physically meaningless. As for if you change the initial guess a little bit, it will give you the right answer. So you have to be really careful with what you're getting. So a good way of ensuring that you're getting meaningful results is to interpret what the root means and also to graphically inspect the problem. Also, don't forget to rearrange the function from f of x equal to some value to f of x minus this value equal to 0. We need the right hand side to be equated to 0. And finally, remember that the fixed point iteration convergence depends on the formal view of x and the initial guess. Okay. Thank you and have a good day.